In 10.1, we're going to look at sequences and then we're going to look at series. So a sequence is just a list of numbers. Typically, a sequence goes from 1 to infinity. If the indices are not written on the set, as in this first example, we can assume that we start at 1. There's two ways to write the formula for a sequence. One is by a recurrence relation or implicit formula. That is where you define a term by the one that came before. We can also get an explicit formula, and that is where the sequence is defined just by the index n. For example, the sequence 1, 4, 7, 10, and so on can be defined using a recurrence relation. And in a recurrence relation, we have to define the first term. So here my a sub 1 is equal to 1 because the first term in my sequence is 1, a sub 2 would be 4, a sub 3, 7, and a sub 4, 10. So we can define subsequent terms, our a sub n plus 1, by the term that came before it, a sub n, and then we're going to add 3. So to get from 1 to 4, I add 3. To get to 4, from 4 to 7, I add 3. 7 to 10, I add 3. So the pattern is adding 3. So when you come up with formula for your sequences, all you're doing is looking for patterns. If I were to write an explicit formula, now the difference is in an explicit formula you cannot use previous terms. You can only use the index n. So for any term, a sub n, I can define it as 1 plus, and then I notice that I'm doing increments of 3, but I have to write it in terms of n, not previous terms. So I use 3 times n minus 1. And if I simplify that, 3n minus 2. Whenever you write a formula, you should always state what n values you're going to start with. And in both of these, I'm starting with n is equal to 1, then 2, then 3, and so on. If you don't state your n values, it will be assumed that you're starting with n is equal to 1. Example 1, we're going to verify the formulas that I came up with for the sequence 1, 4, 7, 10, and so on. So if I look at the first formula, the recurrence relation, the first term a sub 1 is equal to 1. Now when n is equal to 1, that means that a sub n plus 1 is 2. That would be equal to a sub n, which is a sub 1, plus 3. So notice that that's equal to 4, just as we would expect. When n is equal to 2, I'm at a sub 3, which is a sub 2 plus 3, or 7. And then at n equal to 3, we're at a sub 4, which is a sub 3 plus 3, or 10. So our recurrence relation works out. Let's go ahead and try the explicit formula. So notice the explicit formula, 3n minus 2, that just is determined by this n. So these a sub n's, these are terms. The n is an index. So when n is equal to 1, I'm at a sub 1, which is supposed to be 3 times 1 minus 2. And that's equal to 1. So when n is equal to 2, the index n is equal to 2, I'm at a sub 2, which is 3 times 2, minus 2, and that's 4. And you can see when n is equal to 3, a sub 3 is 3 times 3 minus 2, which is 7. And then when n is equal to 4, we're at a sub 4. 3 times 4 minus 2, which is 10. So those formulas work out. Now we can graph our sequences. There's two ways that we graph. One is just a basic line graph, and the other one is a two-coordinate system, like the xy plane. So let's look at the first way that we can graph, and sometimes the graphs help you determine what the formula will be. So I'm going to go and start my graph at -1. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the first term in my sequence is 1. That would be at a sub 1. The next is 4. That's my a sub 2. The next is 7. That's my a sub 3. 10 would be my a sub 4. And this pattern continues. But notice this pattern is add 3 to get to the next, add 3, add 3. So that reminds me of my recurrence relation or implicit formula. To get from one to the next, you add 3 to the term that came before. So we can also use a coordinate system. And here I'm just looking in the first quadrant because my values are all positive, where for every n value, we can get an a sub n. So when n is equal to 1, I'm at 1. When n is equal to 2, I'm at 1, 2, 3, 4. I'm probably going to run out of space. At 3, 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. And I won't do 10. So this is my a sub 1, a sub 2, a sub 3. Notice that on this coordinate system, it looks like my pattern is linear. And if you look at the formula, the explicit formula, it's linear, the 3n minus 2. If I were to graph a sub n equal to 3n minus 2, it would be a line. So we can graph our sequences, and sometimes that will help us determine a formula. But that's actually going to be our biggest challenge here. With sequences, our challenge is coming up with a formula. Example 2, I'm going to look at number 1. I have 1, 2, 4, 8, and 16. Now something to note is that whenever you come up with a formula for your sequences, it may not be unique. There may be many ways to describe the same formula. So when I look at 1, 2, 4, 8, and 16, and I wanted to determine the next two terms, it looks like I'm doubling. 1 times 2, 2 times 2, 4 times 2, 8 times 2. 16 times 2 would give me 32. 32 times 2 would give me 64. So I determine the next two terms in my sequence. The next thing I want to do is I want to come up with a recurrence relation. And I kind of already did. I noticed that to get from 1 to 2, I multiply by 2. To get to 2 to 4, I multiply by 2. So I noticed that to get from one term to the next, I'm always multiplying by 2. So that tells me that's probably going to be my recurrence relation. So remember, you have to define your first term. So my a sub 1 is going to be 1. My a sub n plus 1 is going to be 2 times the previous term, a sub n. And then we usually state the n values. So I'm starting with 1. I didn't have to define it that way, but it works. Remember, this is not unique. So we could check to see if, well, we know a sub 1 is 1. So if n is equal to 1, that means I'm at a sub 2, which is 2 times a sub 1, which is 2. When n is equal to 2, I'm at a sub 3, which is 2 times a sub 2, which is 4. And I could keep going, but it's clear that this works out. So let's try part C. In part C, we want to find an explicit formula. So remember, I cannot use previous terms. I can only use the index n to define. And what I notice with 1, 2, 4, 8, and 16, remember, I'm not looking at a pattern to get from one term to the next. I'm looking at a pattern of the terms themselves. And I notice that 1 is equal to 2 to the 0. 2 is equal to 2 to the 1. I notice that these are powers of 2. 4 is equal to 2 squared. 8 is equal to 2 to the third. So if my first term is when n is equal to 1, and then the second term is n equal to 2, and so on, what I'm trying to do here is see if I can define my sequence in terms of the n value. So what I notice is that the thing that's changing is the exponents on 2. And I want them to match up to these n values. And it looks like they're 1 less. So my exponent is 1 less than my n value. So I'm thinking that maybe my a sub n can be equal to 2 to the n minus 1 power. And then again, this is for n equal to 1, 2, 3, and so on. If I were to check this formula, I would see that it works. A sub 1 is 2 to the 0, which is 1. A sub 2 is 2 to the 1, which is 2. A sub 3 is 2 squared, which is 4, and so on. So that would be our big challenges. Let's try another example. Part 2, this is an alternating sequence. When I work with alternating sequence, what I do is I ignore the plus minus, and I just look at the sequence. In this case, it would be 1, 3, 5, 7, 9, 11, and so on. I just look at the sequence itself, and then I see if I can get some sort of pattern going. But before that, let's look at part A. In part A, I love these roosters. In part A, we need to state the next two terms. So it looks like these are odd numbers, 1, 3, 5, 7, 9, 11. So I know I'm going to have 13 and 15, and I know it's going to alternate positive, negative, positive, negative. So the next two terms would be a positive 13 and a negative 15. And then my recurrence relation, I know that my a sub 1 is 1. It's always the first term. So now I have to figure out a pattern for the remaining terms. So I know they're odd. If I ignore the negatives, then what I'm doing is I'm adding 2 to the one that came before. So if I just wanted to generate the positive numbers and ignore the negatives, what I could do is define, well, let's look at the terms first. So a sub 2 is equal to a sub 1 is 1 plus 2. That would give me a positive 3. Okay? But I need this to be negative. So I'm going to multiply a sub 1 plus 2 by negative 1 to make it a negative 3. Now this is going to happen for all of the terms. All of the terms are going to be the one before. plus 2, but I have to make sure that that's always positive, and then I'll deal with the negatives later. So to make sure these are all positive, what I'm going to do is just put absolute values around the term that came before. So if I take the absolute value of a sub 1 plus 2, and I multiply it by a negative 1, that gives me negative 3. If I take the absolute value of a sub 2 plus 2, that gives me a positive 5. When n is equal to 3, a sub 4, absolute value of a sub 3 plus 2, that's going to give me my 7, but I need it to be a negative 7. So I'm going to multiply by a negative 1. But this is a formula. When I write my a sub n plus 1, it has to be the same for each term. So far I see that I could do an a sub n absolute value plus 2. And then I have to deal with this negative 1. So I'm going to define the exponent on my negative 1 in terms of what my n value would be. Negative 1 to the 1 is negative, and I get a negative 3. Negative 1 squared is a positive 1, and I get a positive 5. Negative 1 to the third is negative, and I get my negative 7. So notice that the exponent on my negative 1 matches up to the n value. So the formula I'm going to use, and remember this is not unique, is the absolute value of a sub n plus 2 multiplied by negative 1 to the n power. And again, that's for n equal to 1, 2, 3, and so on. But don't forget, this is not unique. Let's try C. Again, I'm looking at just the 1, 3, 5, 7, 9, and I notice that these are odd numbers. So typically, whenever we are working with odd numbers, it's 2 times your n value. That will give you an even number. And then you have to figure out if you're going to add or subtract 1, add or subtract 3, add or subtract 5. So you're going to add or subtract some odd number to make it odd. Well, my a sub 1 is 1. So if I take, and this is when n is equal to 1, so if I take 2 times n, that's 2, and if I subtract 1, that gives me 1. When n is equal to 2, I'm at a sub 2. So remember, a sub 2 is going to be 3. I'm ignoring the negatives for now. So does that work? Is it 2 times 2 minus 1? Is that 3? Yes. So I could see that to get the 1, 3, 5, 7, 9, it's going to be 2n minus 1. I just have to deal with the alternating positive negative. So again, I'm going to put a negative 1. I just have to figure out what the exponent on my negative 1 will be. And it has to be written in terms of the n value. Well, my first term is positive, but that's when n is equal to 1. So I can't just have it negative 1 to the n power, because that will make it a negative 1. So I'm just going to subtract 1. So when n is equal to 1, this is going to be positive 1 times positive 1, which is positive 1. Now, this can be quite challenging when you're trying to figure out a formula. Now remember, that's not unique. You can use many different formulas to describe the same relation. However, sometimes it's not even. So some patterns you want to look for when you're trying to figure out a formula for your sequence is an alternating negative positive. So it's always going to be some power of negative 1. You just have to figure out what that power is based on the n values. I have a crazy rooster outside my window. If you have even numbers, it's always 2 times something, or plus or minus 2, plus or minus 4. Odd numbers, it's 2 times your n value, but you're either going to add or subtract 1, add or subtract 3, add or subtract 5, and so on. So again, sometimes it's not possible to find a formula for a sequence. So a question that comes up is, are the numbers going somewhere? Are they approaching a value? Because it is just a list of numbers. So that's where we're going to talk about the limit of a sequence. Unfortunately, we cannot use the definition of limits that we have from Calc 1 because sequences are not continuous. You notice that when we graphed it, there's big gaps between our points. It's just a set of numbers. So since it's not continuous, we can't use that formal definition of a limit just yet. However, we can talk about what a limit is. So if you do have a sequence and it approaches some number L as your n's get larger and larger, then we write the limit of a sub n as n goes to infinity is equal to L. And if that limit does exist, then the sequence converges to that limit. So that would be the number that it's approaching. So if the sequence does not approach a single number, then there's no limit and the sequence diverges. So we're going back to this language of converge and diverge, same language we used when we were talking about improper integrals. And this language of converging and diverging will be in every section in chapter 10 and chapter 11. With sequences, sometimes we can figure out if they converge or diverge. And if we're lucky and our sequence converges, perhaps we can find the limit. But as you'll see when we go through these sections, sometimes the best we can do is just say it converges. Sometimes we can't even figure out what the limit will be. In this section, to figure out the limit of a sequence, what we're going to do is go back to what we did when we first discussed limits. We're going to make tables of values. And we're going to guess what the limit is based on the table of values. And then in the next section, we're going to look at a more efficient way to compute limits. But for now, because they're not continuous, we're stuck with tables. So example 3, we're supposed to write the first 4 terms of the sequence and make a conjecture about the limit of the sequence. And then we're going to state if the sequence converges or diverges. So the first 4 terms of the sequence, a sub 1, and I'm assuming here that we're starting with n is equal to 1 since it's not stated. That would be 1, and you're going to use your calculator for these. 1 minus 10 to the negative 1, which is 0.9. A sub 2, 1 minus 10 to the negative 2, which is 0.99. A sub 3, 1 minus 10 to the negative 3, 0.999, and already I can see what the pattern is. A sub 4, 1 minus 10 to the negative 4, 0.9999. So it appears that as my n's are getting larger and larger and larger, the terms of my sequence are approaching 1. Okay? But this is just a guess. So I can say that the limit appears to be 1. And that means that this is going to converge. So our sequence converges. Let's look at B. So a sub 1, 1 minus 10, and I have negative 9. A sub 2, 1 minus 10 squared, negative 99. A sub 3, 1 minus 10 to the third, negative 999. And already you can see the pattern. A sub 4, 1 minus 10 to the 4, negative 9999. So I notice that as the ends get larger and larger, my terms of my sequence are approaching negative infinity. So this limit, the limit appears to be negative infinity. Which means that this diverges. Let's look at another example. In example 4, we want to use a calculator to make a table of the first 10 terms, and then state a plausible limit or explain why the sequence diverges. So here my sequence, a sub n, and notice that this is an explicit formula. A sub n is for n minus 1 over n for n equal to 1, 2, 3, and so on. So I'm going to make a table where I'm going to put in my n values, and I'm going to get back an a sub n. So by calculator, if I put in 1 for n, I get 3. If I put in 2, I get 3.5. And then I might have to round at 3. And I'll just go 2 decimals if I have to round. 3.67. 4. I have 3.75. When n is 5, I'm at 3.8. 6, 3.83. Looking at these terms, it looks like it's approaching 4. So let's do some more. 7. I have 3.86. 8. 3.88. 9. 3.89. 10. I have 3.9. So it appears that my terms are approaching 4. The problem is, have I gone far enough? How do I know it doesn't get larger than 4? How do I know that it's not going to go 4.1, 4.2, and so on? Well, let me just put in 50. And that gives me 3.98. So again, all I can do is state that a plausible limit is 4. So the plausible limit is 4. I can't say that that's what the limit is, because I can't use any of the limit formulas that I have from Calc 1 since these are not continuous functions. So let's move on. We're going to talk about the difference between a sequence and a series. And this is extremely important. Sometimes people get things confused. Remember, a sequence is a list. A series is a sum. And that's the big difference. Sequence, list, series, sum. But what an infinite series is, it's actually going to be a sum of the terms of a sequence. And so this sum is going to go on to infinity. So we can use our sigma notation that we have here to write the sum from k is equal to 1 to infinity of a sub k. Notice that we're using k instead of n. It's just a variable. You can use whatever you want. The reason we use k is because sometimes our series will not be infinite. It will not approach infinity. Sometimes it'll just approach some number n. So we have what's called an infinite series, and that approaches infinity. However, instead of looking at an infinite series, what we can look at is a sequence of what we call partial sums. And we're going to look at that as being our S sub n's, S for sum. What a sequence of partial sums is adding up the terms of a series, but only to some index n. So for example, S sub 1 is just your A sub 1. S sub 2 says add the first two terms up. So A sub 1 plus A sub 2. S sub 3 says add the first three terms up. So in general, S sub n says you're going to add up the first n terms. So now notice that we're starting with 1 and we're ending with n of our series. And our sequence of partial sums is going to help us to determine when an infinite series converges or diverges. So what we're going to do, and the strategy is similar to what we did with our improper integrals from 8.9. You can think of this summation as like an integral symbol. It's improper because of the infinity. So what we're going to do is we're going to look at the sum, and we're going to substitute n for the infinity and look at the limit as n goes to infinity. So again, exactly what we did in 8.9. And then we're going to look at that summation, which is just sum S sub n. If that has a limit, then the infinite series converges. So if you have an infinite series, a summation going to infinity, to determine whether it converges, you just have to take the limit of the partial sums. So if the partial sums diverge, then the series will diverge as well. Example 5, we want to find the first four terms of our sequence of partial sums, and then we want to find an expression for our sequence S sub n. Okay, now remember S sub n, that is a sequence of partial sums. So what we're going to do is we're going to find an explicit formula for our S sub n, since it's a sequence. So we have this summation 1 over k times k plus 1. So our sequence, our A sub k, is 1 over k plus 1. And here our k values are starting at 1, 2, 3, and so on. So the first four terms of the partial sums would be S sub 1 equal to A sub 1. That's just 1/2. S sub 2, that's going to be A sub 1 plus A sub 2, which is 1/2. Now if n or k is equal to 2, it's 1 over 2 times 3, or 1/6. So it's 1/2 plus 1/6, which would be 4 over 6. And I'm going to reduce that to 2/3. And the reason why is because I have to take these terms and try to figure out what an explicit formula for them. So it's best to keep it reduced. Now S sub 3 is going to be A sub 1 plus A sub 2 plus A sub 3. Notice that that's simply S sub 2 plus A sub 3, which is going to be 2/3. And when k is equal to 3, I get 1 over 12. That would be 9 over 12. And that reduces to 3/4. S sub 4 is going to be S sub 3 plus A sub 4, which is 3/4. If k is equal to 4, 4 times 5 is 20, so plus 1 over 20. I get 16 over 20, which reduces to 4/5. So I got the first 4 terms of my sequence of partial sums. So this is what my S sub n looks like. 1/2, 2/3, 3/4, 4/5, and so on. So that would be my S sub n. And I can see what the pattern is. My S sub 1, right? This is my S sub 1, S sub 2, and so on. So notice that my index, sub 1, sub 2, sub 3, sub 4, sub 5, that's the numerator. So I can see that S sub n, for any n, will be n over. The denominator is 1 more than the numerator, so over n plus 1. For n equal to 1, 2, 3, and so on. I have this formula for my sequence of partial sums. And now if I look at it, it appears. So if you look at that list, 1/2, 2/3, 3/4, 4/5, it looks like my sequence of partial sums is getting closer and closer and closer to 1. So it appears that my infinite series, because that's the only reason why I was looking at the limit of the partial sums, from k is equal to 1 to infinity of 1 over k times k plus 1, it appears that that's going to be equal to 1, that it converges to 1. Okay, well let's look at another example where we have to find a formula for the sequence of partial sums. If I look at this summation, I can see that my a sub k is 0.5k. Sometimes it's nicer to write it as a fractions, especially if you have to find a formula. Some fractions tend to make it easier for us to find formulas. So S sub 1 is your a sub 1, which is just 1/2. S sub 2 is going to be a sub 1 plus a sub 2. So it's going to be 1/2 plus 1/4, which ends up being 3/4. S sub 3, we're going to have S sub 2, which is 3/4, plus a sub 3, which is 1/8, and that ends up being 7/8. And then S sub 4 will be 7/8 plus 1 over 16. So that looks like 15 over 16. So I have 1/2, 3/4, 7/8, and 15 over 16. Let me look at that sequence and see if I could figure out a pattern. All right. Well, if I look at the denominator, I do recognize a pattern there, and it's a pattern that we had when we first started talking about sequences. I see that it's 2, 4, 8, 16. I'm looking at as powers of 2. So 2 is actually 2 to the 1, 4 is 2 squared, 8 is 2 to the third, 16 is 2 to the fourth. So I'm looking at the exponent on the 2 as being the index n. If I were to come up with a formula, so this was our part A, if I were to come up with a formula for S sub n, it looks like the denominator is 2 to the n. So that gives me the 2, 4, 8, and 16. What I notice about the numerator is it's 1 less than the denominator. So 2 to the n, and then I'm going to just subtract 1 from that. So I can write my S sub n, I don't know why there's so many roosters. I can write my S sub n as 2 to the n minus 1 over 2 to the n. Or I could split it up as 2 to the n over 2 to the n, which is 1 minus 1 over 2 to the n. And then that would be for n equal to 1, 2, 3, and so on. All right, so when I look at my terms, it appears that they're approaching 1. Since the numerator is always 1 less than the denominator, the numerator will never get larger than the denominator. And the denominator just keeps growing and growing and growing. So it appears that the limit, and I'm going to use limit notation, it appears that the limit as n goes to infinity of S sub n, which is 1 minus 1 over 2 to the n, it appears that it's equal to 1. And this actually makes sense. If you do put infinity in for n, 1 over 2 to the n is actually approaching 0. So although technically I'm not allowed to do this because these sequences are not continuous functions, I can see that this limit of 1 makes sense. So that tells me that it appears that our infinite series from k is equal to 1 to infinity of 0.5 k, it appears that it's going to equal 1, that it converges to 1. So you may want to pause right now so that you can work on this in class. We want to see if we can find an explicit and a recurrence relation for this sequence. I do notice that it's alternating. And I do notice that the denominator, those would be powers of 3. So I'm looking at explicit first because I can see that a lot easier than the recurrence in this particular case. I'm looking at a sub n being 1 over some power of 3. If n is 1, then that's 1/3, so probably n minus 1. So at 1, I would be at 1. And then I would just multiply this by -1 to the first term is positive, so I could do n minus 1. Remember when I said that this is not unique? Well, oops, sorry, this is supposed to be a minus, not, it looks like an equal sign. What if I were to change it and not start with n is equal to 1? What if I start with n is equal to 0? Then a more efficient way to write this would be 1 over 3 to the n, -1 to the n power. And I can actually play around with this even more, because this 1 over 3 to the n that could be written as 1/3 to the power of n. Notice that I'm multiplying with the same exponent, which means I could write it as negative 1/3 all to the n power. And here n is equal to 0, 1, 2, and so on. So you see that it's not a unique formula. And again, this is just an explicit formula. And I've already given two different formulas just by changing the index. Let's work on our recurrence. So the recurrence relation, I already know that the first term, and I'm just going to start with 1, a sub 1 is 1. So I have to figure out how to describe the a sub n plus 1 term. Well, what I notice is to get from 1 to 1/3, I'm ignoring the negatives, I multiply by 1/3. To get from 1/3 to 1/9, I multiply by 1/3. So it looks like I'm multiplying the previous term by 1/3. But then I have to do with the negatives, right? So I could just make sure that I'm always multiplying by an absolute value here. So I always get the positive 1, 1/3, 1/9, 1/27, and so on. And then do negative 1 to some exponent. It looks like when n is 1, I'm at a sub 2, which is negative. It looks like that will work. Again, remember, this is not unique. I'm going to clean this up just a little bit. So a sub 1 is 1. A sub n plus 1. I'm going to write that as a sub n over 3, all inside the absolute values. It just looks prettier. Times negative 1 to the n. And remember, we're looking at this for n equal 1, 2, 3, and so on. And that's it for this section.